A couple days ago, I hosted a debate between Roohif and John, who goes by Refracted Curvature. Now, Roohif knows that the Earth is a globe, and John, well, he imagines that the Earth is flat. And their challenge was to each present the process of doing celestial navigation, one for the globe and one for flat Earth. And Roohif had a fantastic presentation. He pre-recorded the entire thing, and I'm going to present it right here. Now, of course, the funny thing is, and well, it won't be a surprise, the flat earther had nothing. He ran away and basically agreed that Roohif did it right. The link to the full debate is in the description. Be sure to watch that. And the link, more importantly, the link to Roohif's channel is in the description. Go subscribe to him and tell him thanks.
Good morning, good afternoon, good evening. This is why celestial navigation only works on a globe. Okay, so here is my set of observations for the debate. I've been given an eye height of 32 meters and an index error of 2 arc minutes. And my 3 stars are Achernar, Betelgeuse, and Canopus. And here are the angles and the time that they were taken. Now, the first task is to get the GP of each of these stars at the time of the observation. And GP just stands for geographic position, or sometimes people say ground position. And all the GP is the point on Earth where the star is directly overhead at that point in time. But before we dive into the almanac, we need to understand what the almanac is actually giving us. So here we are looking down on the orbit of the Earth around the Sun, and at the same time the Earth is rotating on its axis. And what we normally consider a full day is the time between local noons. So local noon is just the time when the sun is in line with your line of longitude. And that time is what we've arbitrarily defined as 24 hours. But as you can see in the diagram, because we're in an orbit around the sun at the same time that we're spinning on an axis, then the Earth needs to rotate just that little bit extra to point back at the sun. So a solar day is actually a little bit more than 360 degrees of rotation. Okay, a sidereal day is slightly different. A sidereal day is 360 degrees of rotation. So instead of the time it takes to point back at the sun again, it's the time it takes to point back to a distant star. In much the same way that we've arbitrarily decided that Greenwich Observatory is the prime meridian for the Earth, we've also arbitrarily decided that a particular star in the constellation of Aries is the prime meridian for the celestial sphere. So the purpose of the Nautical Almanac is to map the prime meridian on Earth to the prime meridian of the celestial sphere. And then the positions of all the navigation stars are given relative to that celestial sphere. So we look up our almanac on this particular date, and this will tell us exactly where each star is on that date. So the time of this observation was 5:48 and 12 seconds. So we just need to interpolate between 5 a.m. and 6 a.m. And just notice that each hour is not exactly 15 degrees, and that's because of what I said a minute ago, that a 24-hour day is actually slightly more than 360 degrees of rotation, which means that 1 hour is very slightly more than 15 degrees. Anyway, if I interpolate the time of the observation between 5 and 6 a.m., I end up with a Greenwich hour angle of 19 degrees, 7.8 minutes. And that gives us the relationship between Greenwich's prime meridian and the prime meridian of the celestial sphere, which is that star in the Aries constellation. So on the right-hand side of the page will be a list of all the navigation stars, and we just need to grab the sidereal hour angle and the declination. And that tells us where the star is on the celestial sphere. And now we need to translate that into a latitude and longitude. So in this diagram, we're looking down on top of the Earth, and we've lined up Greenwich at our 12 o'clock position. So from the previous step, the Greenwich hour angle is 19 degrees and 7.8 minutes, and we rotate clockwise to get this orange arrow. Then we apply the sidereal hour angle of 335 degrees and 21.8 minutes, and we end up at the yellow arrow. And that yellow arrow works out to be 5 degrees and 30.4 minutes east of Greenwich, and that's our longitude for the GP. And as for the latitude, there's no need to do any translation. You just grab the declination for the star, which in this case is 57 degrees and 7.1 minutes south, and that is our GP. All right, so obviously we follow the same process for the other 2 stars, and now we have all 3 GPs. So step 1 is complete. All right, next step is to apply the index error correction. And the index error is just the calibration error in the instrument itself. So it's not really that relevant to this process. In any case, let's add 2 arc minutes to our measured angles. And as you can see in the table, the next correction we need to apply is dip correction. But before I use any citations for dip correction, I just want to make sure that I'm using a respected source. So here's a short clip of 10th Man discussing the American Practical Navigator.
All right, so this is a continuation of more research. The American Practical Navigator, an epitome of navigation, the Bible of celestial navigation, and every mariner has this. The ballers and anti-flat earthers told us to get this book and read it so we can get our heads on straight. So I agreed. I bought 4 copies, different years.
Well, thanks for that ringing endorsement, 10th. This book is so well regarded that it's actually carried on board every US Navy vessel. And the section on dip correction is full of interesting tidbits. If I had time, I'd probably read the entire page. But the main things to take away from this are: the dip of the horizon is the angle by which the visible horizon differs from the horizontal at the eye of the observer, which they are calling sensible horizon, and that's the angle that we're correcting for. It also acknowledges that we have a density gradient, and consequently the ray of light from the horizon to the observer's eye is bent by refraction. It even explains that the horizon is further away than it would be if there were no refraction, and it appears higher because the eye of the observer does not detect the curvature of the line of sight. And it also says that the amount by which refraction alters dip varies with changing atmospheric conditions. And last things on this page are the 2 formulas, the one on the left, which we're going to derive in a minute, and the one on the right, which is an approximation. All right, so let's just quickly run through that formula that we saw on the previous page. So remember that the angle we want is alpha, and it's formed by BAC. And this angle beta is simply 90 minus alpha, because the observer's horizontal, which is BA, is by definition at right angles to the observer's vertical, which is AO. Now, the line AC is tangent line to the horizon, which touches the surface at point D, and the tangent to a circle always makes a right angle to the radius at that point, and that makes ADO a right-angled triangle, and we already know 2 of the angles. So from step 1, alpha plus beta is 90 degrees. Then we know that this angle formed at the center of the Earth is also alpha, which is our dip correction. All right, and step 3 is to do some really simple trigonometry. So the cosine of that angle is equal to the adjacent, which is the radius, over the hypotenuse, which is the radius plus the observer height. And that's our formula. But I guarantee you that all the flirfs are having aneurysms right now, because that line AC that touches the horizon at D is a straight line. But isn't it refracted? Yes. Yes, it is. If we wanted to model refraction on a globe Earth, what we would do is have a circle with a radius of 6371, and we'd model the light rays as a circle as well, but with a much bigger radius. And that radius of curvature for the light ray is something in the order of 40,000 kilometers. So it's a big radius, which means it's not curving very much. Now that number of 40,000 isn't something that I've just pulled from my rectum. It actually comes from directly measuring the vertical density gradient, and has nothing to do with the shape of the Earth whatsoever. But that's a whole video in itself, so we'll just take it as a given for now. So you can see here in GeoGebra, I've drawn the Earth in blue with a radius of 6371 kilometers, and I've drawn the light ray in green with that big radius of 40,000 kilometers. I've also centered it on the horizon just to make the geometry a little easier. So if we wanted to calculate the distance to the horizon and incorporate refraction, we could stick our observer somewhere on the left such that his eye height is on the green line, and then work out the arc length between him and the horizon. Now, it's certainly possible to do that geometry with the two circles, but it's fairly difficult. So you know what would be easier than doing geometry with two circles? It would be a lot easier to do the geometry if there was only one circle, that being the Earth, and one straight line, which is the light ray. So what we do is a very cool little geometric transformation where we straighten out the light ray, but most importantly, we have to keep the relative curvature between the two circles at a constant. So if we straighten out this light ray, this will have the effect of making the radius of the Earth bigger to compensate. And if you want to understand this visually, I've modeled it in GeoGebra, and you'll see that as I move the slider, the light ray flattens out completely, but because we have to keep the relative curvature the same, then the radius of the Earth needs to get bigger to compensate. And this is how we get 7/6R. It's just a geometrical transformation. It takes two curves and turns them into one curve and one straight line. And this allows us to draw a straight line tangent to the horizon, but we just have to do it with a bigger radius. Anyway, so back to our formula for dip correction. So on the previous slide, we talked about the 7/6R radius multiplier. Well, 7/6 equals 1.17. But the Nautical Almanac uses a slightly larger radius multiplier of 1.2. So instead of using a radius of 6371 kilometers, we use a radius of 7,645.2 kilometers. So for our observer height of 32 meters, we work out a dip correction of 9.946 arc minutes using that formula that we just derived. I've also plugged it into the approximation formula, and you'll see that we basically get the same value, so 9.94 arc minutes. What I found quite funny though is that the dip correction table in the almanac gives a figure of 10 arc minutes rather than 9.9, even though it says explicitly that the numbers in the table were calculated using that approximation formula. Super weird, but we'll go with 10 arc minutes for our dip correction. The unfortunate news for my Flurf opponent, though, is that if he wants to use the dip correction values from the almanac, he's going to have to accept that they were derived from the Earth being a sphere and that refraction was incorporated. Or, of course, he's welcome to come up with his own geometry for flat Earth dip correction. Okay, almost done. So the next correction we need to make is for refraction. So now that we've corrected for horizon dip, the angle we measured with the sextant is now relative to horizontal. But we still need to correct for the fact that the light from the star has also traveled through our atmosphere to reach our eye. Now, the fact that there is a refraction adjustment at all is a little bit of a problem for my opponent because he's of the opinion that an angle requires two straight lines. But in the real world, we know that the path that the light takes is curved, and we just make a correction for it. Because if you remember back to the dip correction page from the American Practical Navigator book, it said, "For the eye of the observer does not detect the curvature of the line of sight." So the refraction correction is the calculated angular difference between the apparent position of the star and the actual position. That is, the difference between the angle at which the light comes into the lens, which is this projected line of sight, and the angle at which you would observe the star if there was no atmosphere, which would be a straight line between the sextant and the star. In any case, the formula that calculates the refraction adjustment is given by the refractive index of the air at the surface, -1, all divided by the tangent of the elevation angle. We don't have time to go through the derivation for it, but just be aware that this is only an approximation because it ignores the curvature of the atmosphere. Okay, now the refractive index of air at the surface varies, but the typical value given is around 1.000280. And if we plug that into our formula and convert it from radians into arc minutes, we get the formula at the bottom, which is 0.96 divided by the tangent of the elevation angle. So for Achernar, we get half an arc minute. For Betelgeuse, we get 2.4 arc minutes. And for Canopus, we get 1.2 arc minutes. And if we compare it to the values given in the almanac, we can see that they are pretty much correct. So Achernar was 63 degrees, Betelgeuse at 22 degrees, and Canopus at 39 degrees. So now we've made all the necessary corrections. All we need to do is add them to the measured angles to get our true elevation or true altitude. Okay, so the next step is to work out how far away over the surface we are from the GP based on our elevation angle. Now, I'm sure you've heard two phrases thrown around before, and they are minus from 90 and 69 miles per degree. But where do these come from, and what is the geometry that explains them? Now, the minus from 90 part is pretty simple. We've got our observer at the 12 o'clock position here again, and he's measured an altitude angle to a star, and we'll call that angle alpha. Obviously in this diagram, the red dotted line is the observer's horizontal and the black dotted line is his vertical. So they are perpendicular to each other. So the complement to that angle alpha is angle beta. So beta is equal to 90 degrees minus alpha. And that is where the minus from 90 phrase comes from. Most flat earthers think it's a right angle triangle between the observer, the GP, and the star, and that's just not the case. The minus from 90 has absolutely nothing to do with the GP. It's simply giving us the angle beta, which is called the co-altitude, and that's the angle that we really need when we're doing celestial navigation. So tools like a theodolite can measure the co-altitude angle directly because it's on stable ground, can easily establish a vertical reference. A marine sextant, on the other hand, is presumably on a boat that is rocking around on the ocean, so it can't establish a stable vertical. And that's why it uses the horizon as a reference point and then adjusts that angle up to horizontal using dip correction. All right, anyway, where do we get 69 miles per degree? Well, that comes from the fact that the stars are an enormous distance away, such that the light coming from the star is arriving at the observer and at the GP in parallel lines. So those two yellow lines are parallel. What we can do is move that angle beta down to be at the center of the Earth. And now what we have is a sector of a circle. And that's how we'll work out the distance over the surface between the observer at S and the GP at G. So let's say the altitude angle that we observed was 60 degrees, which means our co-altitude angle beta is 30, and therefore the angle it forms at the center of the Earth is also 30 degrees. So what is the distance between the observer and the GP? Well, that's just the proportion of the whole circle. So if our angle is 30 degrees, then that is 1/12 of a 360 degree circle. So the arc length of that sector is simply 1/12 of the circumference of that circle. Pretty easy. And the circumference of a circle is obviously a function of its radius. So let's plug in 3959 miles as a radius. The circumference is 2 times pi times the radius, which is 24,875 miles. And 24,875 miles circumference on a 360 degree circle is 69.1 miles per degree. And this linear relationship between the angle and the distance from the GP is derived from the Earth being a globe and only if the stars are very far away. So one of the big challenges for my opponent is to show the geometry for his model that justifies this 69 miles per degree. Okay, so you can either use the 69.1 miles per degree or 111 kilometers per degree, or like I've done here, use 60 nautical miles per degree. And that will give you the distance you are from each of the GPs. All right, final step, and this part really is the nail in the coffin for flat Earth. The final step is drawing circles of equal altitude. And a circle of equal altitude is simply the set of all points on the surface where the observer would measure that elevation angle to that particular star. And the observer could be at any point on that circle. So in this example on screen, let's say the GP of the star is over Louisiana. We need to find all the points on the surface that are, for example, 1,000 nautical miles away from the GP. So the question is, what formula am I going to use? The Haversine formula. All right, the Haversine formula determines the great circle distance between 2 points on a sphere, given their longitudes and latitudes. Important in navigation, it is a special case of a more general formula in spherical trigonometry, the law of Haversines, that relates the sides and angles of spherical triangles. In fact, more correctly, I'm going to be using the inverse Haversine formula. So the Haversine formula gives you the distance between two known points, where the inverse Haversine, you give it a latitude and a longitude, and then you tell it a distance and a bearing, and it will tell you the coordinates of where you will end up. Now, I would like to plot my circles in Google Earth, but the built-in circle tool on Google Earth actually uses a slightly different formula called the Vincenti formula, which takes into account the slight oblateness of the Earth. But the correct formula for celestial navigation is the Haversine, so I ended up writing some Python code to draw my circles for me. Here's what it looks like in Google Earth. And where these circles intersect is my position fix. So this is it, zoomed right in, just so we can see how tightly these three circles intersect. So my position fix, which looks to be accurate to within about 2 nautical miles, is 31 degrees, 11.1 minutes south, 15 degrees, 36.9 minutes east. And just to finish things up, I'll repeat the questions I had for my opponent during this presentation. Question 1, what is the geometry that justifies dip correction on a flat Earth? Question 2, why is there a refraction correction in the almanac if angles require straight lines? Question 3, what is the geometry that justifies 69 miles per degree on a flat Earth? And question 4, on what map is my opponent drawing his circles of equal altitude?